Hello. I'd like to talk to you today about the scientific awakening. Sometimes it's called the scientific revolution, but it is really a product of the Baroque period. Just as Baroque was elaborate in its investigation of music and art, in its use of literary devices, so now we're going to see how during this period of time of change, of forward-looking mentality, we see the development of the scientific method. Roughly, we're going to talk about the period from 1550 to about 1700, and I've already said that corresponds to the Baroque period. Science, as we know it today, was called natural philosophy back in those days, and it really wasn't called science until the 19th century. Nevertheless, I'm going to use the word science because that's what we're used to. Science, the word, actually comes from Latin, the Latin word for knowledge, which is scientia. Just to show you how complex science is today, let's take a particular field. Here's a list of all of, not even all, just many of the different scientific disciplines. And let's take chemistry. And if we look at just that one field, we have all of these subdivisions within chemistry. It's just an amazing level of subspecialties. And therefore, what we have is a complexity that has just grown and grown and grown because science has become one of the most important parts of our civilization. What we're going to talk about today, the scientific revolution or scientific awakening, is really about two things: thinking in new ways and discovering truth in new ways. So it's thinking and methodology. It laid out the basis for our modern world as a rational, ordered place. It shifted the nature of discourse from what is called deductive reasoning, philosophical, to empirical reasoning or empirical discovery, which is inductive reasoning. Its influence, that is science, was felt in government, commerce, philosophy, education, ordinary discourse, and many, many other areas besides. Well, let's just pause for a moment and think about where we are. The Renaissance was a period that looked backwards. Look back to ancient Greece and Rome. It tried to recapture classical art, architecture, and thought. The scientific revolution and the Baroque period did not look backward. It started to look forward. Therefore, this period of time is what we will call the beginning of the modern era. A few definitions. Science seeks to understand what nature is like, not to fabricate or change nature, but to understand its true nature, what it really is. In contrast, technology seeks to manipulate nature or manipulate the world for human benefit. So science is not a manipulation of nature, it is merely an understanding of nature, whereas technology is the manipulation. It's interesting that the word for art and technology anciently was the same. The word is techna, which shows the similarity between art and technology. Technology and science were largely independent up until the late 1900s, and therefore we can see that art and technology can move forward, whereas there are periods of time when science gets tied up with untruths or gets roadblocked or some other problem and it doesn't progress. And of course that's what happened during the Dark Ages. The understanding of nature was not considered to be important, and therefore science was slowed. Which deals more with truth and falsehood, science or technology? Well, clearly it's science. Science deals with what is nature truly like. Technology doesn't care about truth, it only cares about what works. And once it works, then it becomes true. But the basic nature of science is relatively unimportant for technology. Why was technology able to move forward and science was stagnant? Because technology still was motivated by the needs of people, whereas science was motivated by an intellectual need to understand nature. And during the medieval period, it was believed that religion gave all of the needs, satisfied all of the needs to understand nature in the world. But as we leave the medieval period and go through the Renaissance, then we start to see an awakening of a need to understand science as it truly is. Thomas Kuhn, a modern writer, has discussed scientific revolutions. And there have been several revolutions. The awakening occurred in the Baroque period, and then some changes in various domains of science. This is what Kuhn says. A science such as astronomy operates under a paradigm, such as Ptolemy's geocentrism. Most work is on normal science, the solving of standard problems in terms of a reigning paradigm. But anomalies that the paradigm can't explain accumulate and eventually make the paradigm unsustainable. Then science enters a revolutionary phase as a new paradigm, such as Copernicus's heliocentrism, comes to seem more plausible. Defenders of the old order, who cannot accommodate the change and may not even understand the concepts in which it is expressed, gradually die out, and a new paradigm is left in control of the field. Then the process repeats itself. And we've seen that happen many times throughout the history of the world, where science has to make revolutionary changes because the paradigm has changed. We'll talk about that more in a later lecture. Well, let's talk about what the universe was like going into the scientific awakening. It was based on the Aristotelian universe, and that is, the method for finding truth was deductive logic. That is, you get a few basic premises, and then all truth is determined as it follows logically from those basic premises. Motion was observed by Aristotle to be a deviant condition. Rest was considered to be the natural condition. And everything seeks its natural state, and therefore things slow down and eventually stop, according to Aristotle. Aristotle believed that matter consisted of earth, air, fire, and water, those four elements, that the heavens are really different material from the earth. They're not made out of earth, air, fire, and water. They're made out of a fifth material, a light, airy, perfect material that's called the quintessence, the fifth material. And the planets and the stars are in crystalline spheres that progressively move away from the earth. The earth is the center, and all of these spheres are rotating in uniform motion. So what was science before the scientific revolution or the awakening? Based on Aristotle. And experimentation was not done. Rather, observation was the method of discovering truth. Aristotle reasoned that if you do an experiment where you hold things artificially constant and let one thing vary, then you have changed nature by the nature of the experiment. And therefore, you cannot really determine what nature is because you have changed it as you did the experiment. Hence, for Aristotle, the only way to discover truth would be by observation. Natural philosophy, before the scientific awakening, was part of religion, theology. So theology, or theologians or philosophers, were those who you asked about the truth. It was not until much later, with the solidification of the scientific method, that scientists became the people that you went to and quizzed about truth. During medieval times, there were two areas of investigation. One of them was alchemy. Alchemy was flawed because one of its basic assumptions was that all solids consisted of sulfur and mercury, and therefore you just shifted the composition of sulfur and mercury to create all of the other solids. Astrology was also a powerful scientific investigation, and that science or pseudoscience said that events on the Earth are determined to some extent by the position of the stars and the planets and the moon. We're going to look at several critical or important scientists, and each one of those made a very important contribution. The principal ones that we will discuss are Copernicus. He challenged the basic Aristotelian theory. Galileo, who was able to link experiments and math together. Bacon, who gave us the modern scientific method. Descartes, who gave us theoretical science. Newton, who showed that you could apply laws developed on Earth to the entire universe. And Lavoisier, who developed methods for the quantification of experiments. First, let's talk about astronomy. It was considered the basic science. It was an early study by the Mesopotamians and the Egyptians, and that study of the stars and the moon and the sun has come down to us even today. But it was critically important at the beginning of the scientific revolution. Copernicus, Brahe, Kepler, and Galileo each made significant contributions. Here is a little video that talks about some of those early contributions.
The Sun, the center of the universe. The Earth, just an ordinary planet orbiting the Sun, like all the other planets. With this bold insight, the 16th century astronomer Nicholas Copernicus ushered in a fundamentally new view of our solar system. It was a scientific revolution. But it was not until half a century later that the German mathematician Johannes Kepler, using observational data provided by the Danish astronomer Tycho Brahe, succeeded in drawing an exact picture of the solar system. Since time immemorial, man has taken an interest in the heavenly bodies and sought to understand the rules by which they moved. It was soon noticed that most stars seemed not to move relative to each other. These were known as fixed stars. Where they formed conspicuous patterns in the sky, they were grouped together in constellations. Mythological significance was attached to these groupings. In the course of a night, the stars revolve in a circle around the pole star, or at least they seem to. For today we know that it is really the Earth that moves. Greek philosophers regarded the circle as the perfect form, and at the center of this circle, they were sure, was the Earth immobile. But it was also noticed that some stars did move relative to the others. These were called planets, after the Greek word for wanderers. Curiously, sometimes some of these planets seem to be moving backwards. Mars, for example, when observed from Earth, moves slowly from west to east for months, then seems to come to a halt and move east to west for a few weeks before continuing in its original direction. In order to keep Mars conceptually on a circular orbit, which they regarded as ideal, Greek astronomers hit on the idea that these planets might move on circles within circles, known to mathematicians as epicycles. In around 100 AD, the astronomer Claudius Ptolemy, who lived in Alexandria in Egypt, summarized the work of the Greek astronomers before him into a system that was to hold sway for more than 1,000 years. In this Ptolemaic system, the Earth is at the center of everything. All the celestial bodies revolve around it. Ptolemy assumed a total of 70 circular movements, all going on at the same time independently of each other. This system allowed him to predict the positions of the planets with reasonable accuracy. During the Middle Ages, the Arabs brought back to Europe the knowledge which they had inherited from the Greeks. From then on, the Ptolemaic system determined the world view of the Catholic Church. But could God's creation not be explained rather more simply? This question occupied the Polish scholar Nicholas Copernicus in the early 16th century. After years of calculations, he came to the conclusion that all the planets moved at uniform speeds in orbits around not the Earth, but the Sun, which he thought was at the center of all things. But he had no way of proving this. The Catholic Church rejected the Copernican system and placed his writings on the index of banned books. The German reformer Martin Luther didn't think much of the new theory either. For him, Copernicus was just a fool. Even so, Copernicus had his supporters. One of them, a teacher at the Protestant University of Tübingen, was the astronomer Michael Messlin. He had a student named Johannes Kepler. Johannes Kepler was born on the 27th of December 1571 in Weil, a small town in southern Germany. Although his parents were poor, he was able to attend school. The Protestant state of Württemberg provided all of its children with 3 years of free education. It was soon realized that young Johannes was a bright boy, and he was sent off to Tübingen University with excellent school grades. There, Michael Messlin fired his interest in mathematics, astronomy, and the Copernican system. Young Kepler had wanted to become a pastor, but now he felt himself called upon to provide a proof of Copernicus's theories. It was also Messlin who persuaded the 23-year-old Kepler to go to the Protestant Austrian city of Graz, where they needed not only a good mathematician, but a Protestant mathematician. One of Kepler's responsibilities in Graz, alongside mathematics, was to produce an annual calendar and horoscope. But Kepler was not interested in putting the exploration of the heavens to such banal use as making earthly predictions. In 1596, he published his Mysterium Cosmographicum, The Secret of the Universe, in which he defended the Copernican system, but still he had no proof. One man who thought he did have proof was the Danish astronomer Tycho Brahe. Not of the Copernican system, but of the Tushonic system, named after him. This still had the Earth in the center, but he thought it was orbited only by the Sun and the Moon. All the other planets, in the spirit of Copernicus, went round the Sun. Brahe found that his model would precisely explain the planetary movements as seen from the Earth, except for that of Mars, which still showed irregularities. Brahe had at his disposal the best observatory of the age. His patron, King Frederick II of Denmark, had even given him the use of the island of Fehn for just this purpose. Here, Brahe was able to observe the night sky undisturbed. His rapidly growing and very accurate database made him famous throughout Europe. But when Frederick died, Brahe's days on Fehn were numbered. The new king, Christian IV, was no longer willing to finance this often domineering astronomer. Brahe left his observatory, island and homeland in disappointment. 2 years later, the man with the golden nose, he had lost his own in a duel, was wandering around Central Europe when he found a new sponsor. He became court astronomer to the Holy Roman Emperor Rudolf II in Prague. Some 30 kilometers from the city, in Benátky Castle, Brahe set up a new observatory, with the best instruments money could buy. What he lacked was a capable assistant who could derive the definitive proof of the Tushonic system from his extensive database. Kepler applied for the post and got it. He had already had to leave Graz after the city was reoccupied by Austrian Catholics. Any Protestants had either to return to the old faith or clear out. In the summer of 1600, Kepler arrived in Benátky Castle and took up his employment with Brahe. Relations between the two men were tense from the outset. Brahe regarded Kepler as a mere assistant, someone to whom he could delegate mathematical tasks. A human computer, in other words. Kepler, though, was a sensitive man, and Brahe's domineering manner irritated him. Quite apart from that, he thought the Tushonic system was plain wrong, but he kept his mouth shut on that score. He had come to Prague to make use of Brahe's observational data, the best in existence, and he wanted to keep his job. Then, just a year after his arrival, things suddenly changed with the unexpected death of Tycho Brahe. On his deathbed, Tycho had implored his assistant to fight for the final recognition of the Tushonic system, but Kepler was unable and unwilling to keep this promise. Now, as Brahe's successor at the court of Emperor Rudolf II, he found himself in possession of papers which would finally ditch any view of the universe, including the Tushonic, which placed the Earth at the center.
Here we can see plotted out the path of Mars, one of the problems that we get in the earlier Aristotelian or Ptolemaic version of the universe. We see that as Mars goes around the sun, viewed from the Earth, we see that Mars happens to go backwards. It has a retrograde motion, and that was very confusing. People did not understand how Mars could be going around the Earth in a circular orbit and have this retrograde motion. Ptolemy gave us a method for explaining that, and it was called epicycles. So that when Mars goes around the Earth, instead of going in a simple circular orbit, it actually goes in a little curlicue orbit around. And if you do that, if you assume that method, then you can calculate quite closely the actual motion of the planet Mars. And that's what was done by Ptolemy in the early medieval period. Copernicus, in the beginning of the scientific revolution period, made a new proposal, and his proposal was that the sun was at the center of the universe. The Mercury, Venus, the Earth, Mars, Jupiter, and Saturn all orbited around the sun in circular orbits. The moon orbited around the Earth. And therefore, using this model, Copernicus was able to get some easier calculations and some simplifications. But Copernicus's model still had some problems. One of the problems is common sense. We see the sun come up in the east and set in the west. That's not explained very easily by the Copernican model. Not only that, Copernicus would say that the Earth spins on its axis. And I don't feel any spinning. I don't think you do either. And that was kind of strange. How could you, why is it that we do not feel the spinning of the Earth? And as the Earth goes around the sun, there would at the equator be about 1,000-mile-per-hour wind. And clearly that's not the case either. So some of those problems continued with the Copernican model. Not only that, to get the calculations exact, Copernicus could not eliminate the epicycles. He still had to retain some of them, and we know now the reason is because Copernicus used circular orbits rather than actual orbits that are elliptical. There was another problem, and that is that the scriptures tended to contradict the Copernican view. Let's read that scripture that was pointed to over and over again by people in the church who were critical of Copernicus. In Joshua 10:13 it says, "And the sun stood still, and the moon stayed until the people had avenged themselves upon their enemies. Is not this written in the book of Jasher? So the sun stood still in the midst of heaven, and hasted not to go down about a whole day." Clearly, that means that the sun is traversing across the heavens. Well, this confused people, and certainly they did not accept the Copernican model as being consistent with this. Too bad they didn't have the Book of Mormon. It would have explained it. Here in Helaman it says, "And thus according to his word the earth goeth back, and it appeareth unto man that the sun standeth still. Yea, and behold, this is so, for surely it is the earth that moveth, and not the sun." So it was understood in the Book of Mormon, but not in the Bible. Nevertheless, that made life terrible for Copernicus. Some of the problems that Copernicus encountered were solved by another model proposed by a fellow named Tycho Brahe. He was a Dane, and he did a revision of the Copernican model, and in his revision, he said that all of the planets except the Earth revolve around the sun, but the sun itself revolves around the Earth. And therefore, this two-centered solar system, the Tychonian model, made some simplifications and gave Tycho Brahe some interesting notoriety. Nevertheless, it was not accurate, and it still retains some problems in calculation. But Tycho Brahe had a student named Kepler who, upon Tycho Brahe's death, assumed control over the astronomical area and the calculations and the data that Tycho Brahe had developed. Kepler then took all of that information and tried to fit it into planetary orbits in a nested system, and he tried to use geometric solids because he was a strong believer in Pythagorean theorem, or in Pythagoras' concepts of small whole numbers and simple geometrical shapes. But he couldn't quite do it until one day he had a discovery, and here's a video that talks about that discovery.
Kepler looked particularly hard at Mars, whose orbit Brahe had measured. He sought to understand the planet's path in Copernican terms. After 4 years of hard work, he realized this wasn't possible. There was only one conclusion: something in Copernicus's theory was wrong. As a result, Kepler came to formulate his first law, which dispensed with a 2,000-year-old tradition. The planetary orbits were not circles, but ellipses, with the sun at one focus. Kepler also slaughtered another sacred cow, namely the idea that the planets moved at constant speeds. In reality, they move faster when nearer the sun than when further away. In his second law, he showed, again using Brahe's data, that an imaginary line between a planet and the sun sweeps out equal areas in equal times.
Yes, there are 3 laws developed by Kepler. The first of those laws assumes an elliptical orbit of the planet around the sun. The second talks about the position or the length of the ellipse, and it talks about equal areas being swept out in equal times on both sides of the ellipse. And then the third law talks about the ratio of the periods to the radii, and it turns out that the periods, their ratio is a square and the radii is a cube. And because of all of those laws and the relative simplicity of the laws, Pythagoras' concepts were confirmed in Kepler's mind, and Kepler proposed those laws, which are the laws that we use today. The next major contributor was Galileo. It's interesting that Galileo had read Copernicus and had decided that Copernicus was right. He also was informed of the new concepts of Kepler, but he rejected them. So one of the first things we need to realize about Galileo is that he was not always correct, not completely correct. We should also realize that he was a hard-headed, stubborn person who just happened to be brilliant. He's obviously an Italian philosopher, mathematician, astronomer, sometimes called the father of science, or at least from the empirical standpoint, that is, using experiments and the senses to discover things. And he is one of the, maybe not the inventor, but certainly a perfecter of the telescopes and astronomical observations. One of the early things that Galileo did was study pendulums. He was looking at a chandelier that was swinging in a church, and he wanted to know the period of the swinging of the chandelier under various conditions, large swings, small swings, and he needed to have a clock, so he used his own pulse as a clock, a very innovative concept, and he was able to use that pulse to time the swinging of the pendulum, the chandeliers. And then he reduced that to mathematical laws and was able to express the results mathematically. In fact, Galileo said, "The universe stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it." Again, a very strong Pythagorean viewpoint, as Pythagoras was a strong advocate of mathematics. Well, what are the contributions of Galileo? One of them is that he directly challenged an Aristotelian concept of motion. Aristotle said that a heavy body would fall much faster than a small body. Galileo went, as legend would have it, to the Leaning Tower of Pisa, dropped a large and small object off the tower, and had his students note when they arrived, and they both hit the ground simultaneously. Therefore, Galileo corrected the view of Aristotle. Galileo also made significant contributions to optics. He had heard about the grinding of lenses and arranging them in a tube to study very small things, that is the microscope. And he figured out how you could do grinding of lenses and arranging them in tubes to create a telescope. He then used the telescope to do some investigations of the astronomy. And here we see a picture of sunspots. We think that that's not very important, or at least what is so important about sunspots. But remember that in the Aristotelian world, the sun was perfect and could not have spots, because a spot would be indicative of some imperfection. And therefore, the recording or observation of sunspots would have been a major defeat for the Aristotelian method. In addition to that, Galileo observed the moons around Jupiter. Here we see what he saw in several days in January of 1610. And you can see that sometimes he saw Jupiter with little spots on the left and the right, and sometimes only on the right, different numbers of spots. And so those Galilean moons were all discovered by Galileo. He called them the Medici moons rather than the Galilean moons. He also discovered the rings of Saturn, and what he saw was the Saturn with two fuzzy spots on either side, and he reasoned that that would be the rings. He also talked about the phases of Venus and showed how that would be best explained by a solar-centered universe rather than an Earth-centered universe. Galileo was criticized by the church and criticized by others in his community. But he was dismissive of some of the arguments that were used against him. And he said, "God is the author of two great books, the book of Scripture and the book of nature. These cannot be in conflict. So any apparent contradictions come from fallible human interpretations. Scripture is a book about how to go to heaven, not a book about how heaven goes." Very clever wording. Well, what really was the argument then between Galileo and the church? In 1632, Galileo published a book called Dialogue Concerning the Two Chief World Systems, Ptolemaic, and Copernican. He did this over some minor objections from the church. In particular, Pope Urban VIII, who was a friend of Galileo, had requested that Galileo present the Copernican view only as a theory and not as a proven fact. But in the book, Galileo has several people speaking, and the smart person always defends the Copernican view, and the dumb person, Simplicio, defends the Ptolemaic view. Galileo made a serious mistake because he took some of the words that he had gained from personal conversations with Urban VIII, and he took those words and put them in the mouth of the stupid person. That infuriated the Pope, and therefore the Pope called Galileo to Rome. An inquisition was held. Galileo was found guilty of publishing a book in which he advocated the Copernican view as the truth rather than as a theory. It is true that he did that. And it is true that he was told by the church not to do it. The church wanted him to treat it as if it was an unproven fact, because they could still see many problems with the Copernican view. Nevertheless, this church versus science controversy has been built up over the years. Galileo was embarrassed. He was forced to imprisonment in his home, and he died under that house arrest. The church has always had a black eye because of this, and therefore, fairly recently, the church came out with a new finding. In 1992, the Pope authorized the following to be written. Galileo's judges, unable to dissociate faith from an age-old cosmology, believed quite wrongly that the adoption of the Copernican revolution, in fact, not yet definitely proven, was such as to undermine Catholic tradition, and that it was their duty to forbid its being taught. This subjective error of judgment, so clear to us today, led them to a disciplinary measure from which Galileo had much to suffer. These mistakes must be frankly recognized, as you, Holy Father, have requested. And that was published, and therefore, if you like, Galileo was exonerated. Now let's talk about the person who really dug in and developed the scientific method. His name is Francis Bacon. He lived from 1561 to 1626. He was the Lord Chancellor of England. That means that he was the #1 jurist or judge in all of England. And he was caught in some problems of bribery, not necessarily his fault, not necessarily different from others, but he was blamed for some problems, and he therefore resigned his position as Lord Chancellor. This was during the time of James I, and he retired. That gave him sufficient time to dedicate himself to writing and to the development of the scientific method. In this method, he uses inductive reasoning gained from experiments as the method for the discovery of truth. And he counsels people to beware of idols, that is, false things that rise from improper use of the scientific method. We'll explore those in a moment. The first of those idols is the idol of the tribe. This is a human tendency to perceive things from a finite and fallible perspective. In essence, idols of the tribe are human problems. The next is idols of the cave. These are individual weaknesses, not the human race itself, but our own individual likes, dislikes, and personalities. Idols of the marketplace have to do with how we communicate our results. The language might be flawed and therefore give a bad impression. And finally, idols of the theater. These are philosophical systems that might taint or twist the results that we get. So all of those idols are to be avoided. What is the right way, the correct way of doing science? Well, he gives 3 examples. The first is, he says science is like ants. Ants go out and they build up a store of supply. They just get information. They just get facts. It's a person who carries on lots and lots of experiments but never draws any conclusions. The second is like spiders. They build a complex system, beautiful to behold, but it doesn't have any substance to it. In other words, they're all theory and no facts. The best is not either of those extremes. It is in between. Honeybees. They take materials from nature and convert it into materials that are useful for humankind. There's some theory and some practice, but in essence, the real pursuit of science should be usefulness for humans. Okay, now, what are the details of this modern scientific method? First of all, it's based on sensory perception. That is, we get knowledge through our senses. It's called empirical knowledge. It's more reliable than just simply examining the world through logic or theology. The second is that we use manipulation. That is, we conduct scientific experiments. Third, cause and effect must be inviolate. That is, we hold all variables constant except one. That one variable changing, therefore, must be responsible for the differences that we see in the experiment. Therefore, we see a cause and an effect. The theory should be developed after the experiments are interpreted. So you run lots of experiments, you interpret them, and then, based upon all of that data, you then discover what the theory is. You also do inductive reasoning. Inductive means you take lots of little data points and build them into something large. So that inductive reasoning builds up from experimentation. The interpretation of the data is to be unbiased, and that is guaranteed by having different people be able to perform the same experiment and get the same results. And after all of that has been done, the experiments, the theory, and we see repeated evidences of all of those theories, then we can call that a scientific law. So that is the basis of modern science today. It was given to us by Bacon. There's another element to science that was given to us by a Frenchman, René Descartes, about a half a generation after Bacon. He was a rationalist and loved theory. He had an interesting personal quirk. He spent most of his life in bed. He was a hypochondriac, although he was of a weak disposition, and he finally died because of exposure to the cold. But one time while he was lying in bed, he saw a fly buzzing around in his room. And just by thinking about it, he realized that a person could determine the position of the fly at any moment by taking perpendicular measurements from the three walls of the room. And therefore, those 3 coordinates defined spatially where the fly was. That concept was called Cartesian coordinates. Cartesian is the Latin word for Descartes. And then, from that, he developed the mathematics of analytical geometry. Brilliant man. When it came to the scientific method, he said that one should start by getting rid of all assumptions. Go to the basic fundamental knowledge that does not require any assumptions. So we started to think through all of that, and he finally came to the scientific basis where he was thinking, and therefore he knew that he existed. And he stated that in Latin as cogito ergo sum, or I think, therefore I am. I'd like to show you a couple of cartoons that kind of make fun of that, but give it a little bit of meaning for us. Here's a young person who says, I shop, therefore I am. It's kind of funny. Here's another one. I think, therefore I'm underpaid. And another, I think, crossed out, attend meetings, therefore I am. And finally, another one, I react to external stimuli, therefore I am, because these little bugs don't think, they merely react. Well, I hope you don't mind my little joke. René Descartes also believed in a concept called reductionism, and that is simply taking a problem, and if that problem is so complex you cannot solve it, you divide that problem into little tiny pieces until you get to a piece so small and so simple that it can be solved. And then once you solve that one, you begin to build up until eventually you can solve the entire problem. So that process is called reductionism, and it is one of the bases of modern science. Is it always good? Maybe not. If the action of one part of a system determines or influences the action of another part, if you reduce one down and lose that interaction, then you don't understand the entire system. And that concept of reductionism, therefore, should be done carefully to make sure that you don't lose interactions. Is the system always equal to the sum of its parts? Not necessarily if the interactions build beyond what each of those parts does separately. Now let's turn to the greatest scientist who ever lived in the minds of most people. That's Isaac Newton. He wrote a book called Principia Mathematica, and in that book he summarized the laws of gravity, the laws of motion. Many people believe that it is the most important scientific work. We've all heard of the falling apple incident. It is said that Newton observed an apple falling out of a tree and perhaps it hit his head, and from that he rationalized the existence of the law of gravity. Well, let's just talk about where that story comes from and whether or not it might be true. It comes from Newton's niece. She was discussing Newton's life with a French philosopher who had come over to England, and then that French philosopher returned, his name was Voltaire, returned to France and wrote up some writings about Newton and told the story in those writings. So the origin is Voltaire, who got it from Newton's niece. Well, there is some truth to the possibility of this existence even beyond that, because as a young student at Cambridge, Newton was forced to go back to his grandmother's orchard farm when there was an outbreak of the plague and Cambridge was closed. And while back at the farm, Newton did formulate the concepts of gravity and of the laws of motion. Therefore, an apple orchard, perhaps on his grandmother's farm, may have been the inspiration for what we see. No one knows exactly whether it's true or not. Here are Newton's laws summarized for us. The law of universal gravitation simply says that between any two bodies of any size, of any mass, there is an attraction, and that attraction is determined by the mass of the two bodies divided by the distance between them. And there's a gravitational factor that makes all of the units come out right in the right magnitude. Therefore, if the bodies are large, like the moon and the earth, then the gravitational attraction is quite strong. If the distance between two bodies is quite small, then the gravitational attraction can also become quite large. There are three laws of motion developed by Newton. The first one says that any body in motion tends to remain in motion unless acted upon by an outside force. So if you have a ball that is at rest, it will stay at rest. But if you have a ball and you push it and it moves, then it will continue in uniform motion unless acted upon by some other force. And that other force could be it runs into a wall, or perhaps friction slows it down. The second of the laws says that the speed or direction of an object is proportional to the force acting on it. And this is often written as force equals the mass times the acceleration. And this is the law that explains why a large and a small body would fall at the same rate. Newton's third law says that for every action there is an equal and opposite reaction. And here we see illustrated a skateboard. And as you know, if you propel yourself off a skateboard, you'll go forward and the skateboard will go back. One of the implications of Newton's work is determinism. Determinism. That says that all things in the universe follow a set law or a group of laws. It's like a clock. Everything in a clock works in regular order, and therefore it keeps perfect time. And therefore, in Newton's view, the universe was like a giant clock with all of the mechanisms working according to laws. Newton also gave his contributions in optics. He developed the laws of fluid flow, and in fact, he gave us the law for viscous fluids. He also introduced modeling, that is, using mathematics as a predictive method and showing how models could be predicted from those mathematical formulations. Newton was fiercely focused. Here is an account of the way he would do experiments. Newton was driven with a zeal that would unnerve the most devoted scholar, experimenting for days without food or sleep, staring at the sun until the image continued to burn unrelievedly in his head, probing his eye with a darning needle to investigate optical effects. He set out to test the limits of the physical world, and in the process often discovered his own. He was clearly a dedicated experimenter. He said, "I keep the subject constantly before me and wait until the first dawnings open slowly by little and little until the full and clear light." Therefore, he discovers things by just focusing without relief. He said, "I have seen farther than others. If I have seen further than others, it is by standing on the shoulders of giants." And he pointed to several people in the ancient world, like Archimedes, as some of the giants on whose shoulders he stood. What have other people said about Newton? Edmund Halley, the discoverer of Halley's Comet, said, "Near the gods no mortal may approach." He was a personal friend of Newton's. In addition to that, it was said, 100 years after Newton, Napoleon asked his great court astronomer if there would ever be another Newton. He answered, "No, sire, no, sire, for there is only one universe to be discovered." Let's now take a look at a short video that talks about Newton and some of his personal life and some of the things that he discovered.
In 1669, Newton succeeded Isaac Barrow as Lucasian Professor of Mathematics. As part of the requirement for the post, Newton was to be ordained a minister in the Anglican Church. In his studies of early Christianity, Newton became convinced that the doctrine of the Trinity was a fraud perpetrated in the 3rd and 4th century. He was set to resign his post when he received a dispensation. It is a measure of the depth of Newton's spiritual beliefs that he was willing to abandon all he held dear rather than compromise them. His belief in God was the very basis of his existence. Newton's God was a personal God, a creator who was not only over the world but a part of it, a rational God who revealed himself in the workings of nature. The mechanical philosophy of René Descartes had removed God from nature, something Newton found abhorrent. He turned to alchemy in the hope of finding an answer. Alchemy was as old as civilization. Essentially, it was the study of natural magic, a search for the spirit in matter. This spirit manifested itself in physical change, such as fermentation of milk to cheese, the curative properties of herbs, or in the transmutation of metals. Newton believed that he had been ordained to use his God-given genius to reveal this lost wisdom. In 1669, Newton purchased 2 furnaces and converted part of his quarters at Cambridge into a laboratory. Throughout the 1670s and 80s, with the help of his servant Humphrey Newton, he worked long into the night. Humphrey Newton thought him to be a man possessed.
So intense, so serious upon his studies, he ate very sparingly. Nay, oft times he forgot to eat at all. He rarely went to bed till 2 or 3 o'clock, the fire scarcely going out night or day. He sitting up one night as I did another till he finished his chemical experiments. Humphrey Newton.
As intense as his work was in alchemy, mathematics, and physics, it paled in comparison to his studies in theology. Like many men of his generation, Newton thought that mankind in ancient times held wisdom that had been lost over the centuries. He believed that his discoveries in mathematics and physics had been known to the ancient Greeks. Newton became convinced that Pythagoras had accumulated this wisdom from a meeting with the Old Testament patriarch Moses in Sidon. To accommodate this historically, Newton began compiling the chronology of the ancient kingdom. The heart of all Newton's work was the conviction that a rational God had made a rational universe whose laws could be discerned by analysis and mathematics. As his alchemical experiments led him deeper into the search for the spirit of nature, his understanding of the mathematical and physical laws of nature grew more profound.
In essence, Newton, a very complex person, had 3 compelling interests in his life. One of them was natural science, one was alchemy, and the third was Christian theology. Newton did not believe in a 3-in-1 God, the Trinity. That was a problem for him because he was at Trinity College at Cambridge, and there was an oath required of all of the professors that they believe in the Trinity. When Newton offered to resign because he could not support that oath, an exception was made because the supervisors of Trinity College felt that Newton was so valuable that they did not want to lose him. But Newton combined some of the concepts of alchemy with the concepts of natural science. For instance, alchemy believed that there could be forces at a distance, that things could interact without touching. Certainly was not according to Aristotelian science, but that concept of force at a distance is one of the secrets to the law of gravitation, and that may have helped Newton in his formulation of that law. As noted in his preface to the Principia, Newton's desire was to show God's activity in the world. He was raised as a Puritan, devoted much of his time to alchemy and theology, and in fact he wrote much more about theology than he did math and physics. John Locke, another personal friend, said he never knew anyone who had a better command of the scriptures than Newton. And Newton, of course, used some concepts from alchemy, as I mentioned, force at a distance. He was an avid proponent of separate Christ and God, would not accept the Trinitarian belief, and he believed that there was a great apostasy that occurred when the Nicene Creed was formulated. Early in his career, Newton was asked, "What is gravity?" He simply said, "My job is just to identify, not to explain." But later in his life, after having some time to consider it, he then said, "Jesus was beloved of God before the foundation of the world," he wrote, "and had glory with the Father before the world began, and was the principle of the creation, the agent by whom God created all things in this world." To summarize, the spiritual body of Jesus, the first created, was the facilitator for the creation of the physical universe, provided the means via which the cosmos continued to function mechanically, and acted as a medium via which forces acted at a distance without any visible, tangible, measurable mechanism. In essence, Newton is saying God first created Christ, and then through Christ, he created the universe. And there is a force that emanates from Christ that controls all things and is through all things, and that gives the force of gravitational attraction to all things. The very interesting concept, very much like the LDS belief of God and Christ. Well, now I'd like to talk just a little bit about chemistry. When I graduated from school, I graduated with a degree in chemistry. I remember very clearly the very day that I decided to become a chemist. I was sitting in high school chemistry class, and my professor was, the teacher, school teacher, was talking about how atoms are made. And he talked about the Bohr model of the atom. And he said, there is a proton with an electron going around it. And that orbiting electron and the proton of opposite charges give neutrality. And then he said, to make helium, all you have to do is add another proton, perhaps also some neutrons that have no electrical charge, and then electrons around the outside, 2 of them. And I then realized that the elements could all be created simply by adding a proton and an electron with perhaps some neutrons to each previous element. And I thought at the time that might be how God created the universe, that he took these elementary particles which could be exchanged with energy and put them together to create the elements. And so from that time on, I became a chemist. It was a very spiritual occurrence for me, much like I think the spiritual occurrence that occurred with Newton and his discovery of the laws of motion and gravity. There is a tribute, a tomb for Newton in Westminster Cathedral, Westminster Abbey, pardon me, and it reflects a statement by Alexander Pope, who we will talk about. He's an English author. He said, "Nature and nature's laws lay hid at night. God said, 'Let Newton be,' and all was light." Yes, Newton gave us tremendous concepts. John Gribben, however, questions whether Newton was so unique. He said, "Newton's real importance derived from the way in which he pulled together all the various bits and pieces of the new philosophy into a coherent whole. If he had not existed, however, this would have happened anyway, certainly within a generation." Well, I don't know if you agree or not. I think probably it would have all happened, but perhaps not in exactly the same way. Now let's talk about some other people. William Harvey, for instance, was an English physician, and he wrote a book about the movement of the heart and blood in animals, described the function of the heart and the circulatory system, disproved some of Galen's theories. Galen was a Roman physician, lived in the time of the Roman Empire. And again, we can see a person in the Baroque period breaking with tradition and criticizing some of the ancient tradition of Rome and Greece. Finally, let's talk about chemistry. 3 people that I'd like to just briefly mention: Robert Boyle, Joseph Priestley, and Antoine Lavoisier. Robert Boyle gave us many, many laws of gases and physics and chemistry. Priestley, also some very interesting discoveries, but Lavoisier is the one who gave us modern chemistry because he developed quantification. You might ask, why do we care about quantification? Well, it is the way that we determine chemical formulas because they have a very quantitative relationship between them. And it's another way of tying mathematics or arithmetic in with science. Lavoisier was a marvelous man, a Renaissance man. Let's read a discussion of what he contributed. Not for nothing has Lavoisier become known as the Newton of chemistry. Yet he was no single-minded pioneer. During his brief 50 years of life, he not only established modern chemistry, but also found time to occupy, simultaneously, several top-level administrative positions, as well as contributing technical advances in a number of disparate fields: ballooning, the mineralogical mapping of France, urban street lighting, the Paris water supply, the efficiency of gunpowder, and a full-scale model farm, to name just a few. Clearly, he made tremendous contributions, and one asks, how could the French Republic be so stupid as to behead this man as part of the Reign of Terror? He was in fact killed, and the judge who killed him said, "The Republic has no need of experts." We ask, why would he say that? I just can't imagine a judge making that kind of a statement. Well, one of the contributions of this period of time was not just the model and the theory and the concepts, but it was also the introduction of instrumentation and mathematics as a method underlying science. And so we see analytical geometry developed, calculus developed, telescopes and microscopes, the pendulum clock, thermometers, barometers, mechanical calculators, all arising from the concepts developed in this part of the scientific awakening. We also get the formation of the Royal Society, as well as other scientific societies, where people would gather together to talk about science. They were dedicated to Bacon's induction method of studying empirical data. The 12 members represent who's who of early science: Robert Hooke, William Gilbert, William Harvey, Robert Boyle, Christopher Wren, Isaac Newton, and John Wilkins. And they all said their motto was, "On the words of no one," meaning we always have to have data. Therefore, we see the scientific revolution, scientific awakening, as a key part in the history of the world. Don't miss out on these important discoveries in your life. You should be comfortable with science enough to understand it and use it. Thank you very much.